Hey, welcome back to the Deep Dive.
Hello!
Today, we're tackling a really foundational text, one that's fundamentally changing how the internet works. RFC 9000.
That's the one. QUIC version 1, the official spec.
Exactly. A secure general-purpose transport protocol.
Hmm.
And this RFC, well, it's the source.
It is. It's dense, definitely, but it lays out all the core thinking behind QUIC. It's not just what it does, but why they designed it that way.
Right. And that's our mission today, really.
Right.
We want to dive into this RFC 9000 source material, pull out those key concepts, the real nuggets, how it builds connections, how data actually flows, the security, the resilience, getting those insights straight from the source document.
Sounds good. Let's do it.
Okay, so digging in, the first thing that jumps right out from RFC 9000 is QUIC's foundation. It says very clearly, QUIC runs over UDP.
Yeah.
Which, feels weird. UDP is the unreliable connectionless one, usually.
It absolutely does seem counterintuitive, but the RFC explains it, right? It's a very deliberate choice.
For deployment.
Primarily, yes. Think about TCP. It's buried deep in the OS kernel. Updating it is slow, painful. Middle boxes often interfere.
Okay.
So by building QIC on top of UDP, they moved the protocol logic into user space, applications.
Which means faster updates, faster innovation.
Exactly. You can roll out new features much more easily across different apps and devices. The key insight here from the RFC is that they engineered QUIC to be connection-oriented and stateful, even though it's using UDP.
So they built the reliability into QUIC itself rather than relying on the underlying UDP.
Precisely. They added the state management, the reliability, where UDP naturally has none.
Fascinating. Okay, so building state on a stateless layer. The RFC also talks a lot about integrating security and speed right from the get-go.
Yes, and that's another core piece from the spec. QUIC doesn't just tack on security later. It integrates the TLS handshake directly into the initial connection setup.
Okay.
And the explicit goal, stated in the RFC, is to exchange application data as soon as possible, minimize that startup latency.
Which leads to that zero RTT idea.
Exactly, zero round-trip time. The RFC details this possibility if you've connected before and you have the right config cached.
You might send data on the very first packet.
Potentially, yes. Now, the spec is clear. It requires prior state. There are security caveats to consider.
Right. Not always possible.
But the goal is that latency reduction by combining the transport and security handshakes. It's fundamental. And security isn't an afterthought. The RFC specifies authenticating the entirety of packets.
Okay.
And encrypting, quoting here, as much as is practical. That's a stronger baseline than just plain TCP. So how does an application actually use this connection then, once it's up and running?
This is where streams come in, right? That's different from TCP.
Very different. TCP gives you one single ordered byte stream. QUIC, as defined in the RFC, lets you have multiple independent logical channels within one connection. These are the streams.
And there are two types.
Two types defined in the spec. Bidirectional, so data flows both ways.
Like a typical request response.
And unidirectional streams, where data just flows one way. Think notifications, maybe? Applications can open and manage these streams independently.
And the big advantage mentioned in the RFC is avoiding headline blocking.
That's a key engineered benefit, yes. If one stream gets held up waiting for lost data, it doesn't stall the other streams on the same connection.
Unlike TCP, where one lost packet can gum up the whole works.
Precisely. The RFC also details this credit-based flow control system using specific frame types like max stream data for each stream and max data for the whole connection.
To stop one end from just flooding the other.
Exactly. It prevents overwhelming the receiver's buffers. It's quite sophisticated.
So, okay, built on UDP, but RFC 9000 clearly details how reliability and congestion control are baked right into QUIC itself.
That's right. They had to build it all in. The spec talks about ACK frames acknowledgements.
Standard stuff for reliability.
Yep, fundamental for feedback. Letting the sender know what arrived, detecting loss. This feeds the congestion control. The RFC discusses the trade-offs,
How often to send those ACKs?
Yeah. Send them fast, you detect loss quickly, keep congestion control responsive. But send too many, and you're just adding overhead.
A balancing act.
A delicate balance defined right in the protocol spec.
Now, here's something from the RFC that feels very current, essential for mobile, maybe. Connection IDs and mobility.
Oh, yeah. This is really powerful, and the spec goes into detail. Unlike TCP, which is tied tightly to that four-tuple source IP, source port, destination IP, destination port,
Right.
QUIC connections use connection IDs. The RFC explains these IDs are for consistent routing, and the big insight here is what that enables.
Which is?
The connection can survive underlying network changes. Your phone switches from Wi-Fi to cellular, your IP address changes.
Or your home router messes with your port number NAT rebinding.
Exactly. With TCP, that usually breaks the connection. With QUIC and connection IDs, the connection can persist. It's called connection migration.
Okay, so the client moves to a new network path. How does the other end, the server maybe, know it's still the same legitimate connection on this new IP address?
The RFC mandates path validation. It uses special path challenge and path response frames.
So a quick check.
Basically, yeah.
Yeah.
The endpoint getting traffic on the new path has to prove it can receive replies back to that path before fully committing to the migration. Keeps things secure. The spec also mentions servers can suggest a preferred address during the handshake.
Like, hey, next time, maybe connect here instead.
Sort of, yeah. Using a transport parameter, it signals where it might prefer future connections or migrations to go, perhaps for load balancing or better routing.
Okay, makes sense. Finally, how does RFC 9000 say these connections end?
Well, there's the graceful way, using connection close frames. Both sides agree things shut down cleanly.
Standard.
But the spec includes something pretty important for failures. The stateless reset.
Stateless reset.
Yeah. Imagine one end crashes hard, loses all its connection state. It can't gracefully close.
Right, it's just gone.
So it can send this special stateless reset packet. The clever part, detailed in the RFC, is that this packet contains a token derived cryptographically from the connection ID.
Okay.
The peer can verify this token without needing the lost state for that specific connection. It basically says, hey, I've lost my state for this connection ID. You should terminate it immediately.
So it's a robust way to signal catastrophic failure without needing the original context.
Exactly. More robust than how TCP sometimes hangs in those situations.
So looking back at RFC 9000, it really lays out this protocol that, it feels like a reinvention of the transport layer, doesn't it?
It kind of does.
Building all that reliability, security, speed, the mobility, resilience.
Yeah.
But doing it on top of UDP. That layer we usually think of as simple, unreliable.
It shifts where the complexity lives, right? Moves it up out of the OS kernel, largely.
Yeah. The RFC really forces you to think about the implications. So here's a thought, something for you, the listener, to maybe chew on. How does having to engineer all of that, the connection state, reliability, security, flow control, mobility inside QUIC itself, instead of just relying on the OS's TCP stack, how does that change the game for application developers? What new possibilities or maybe new challenges does that open up compared to just building on good old TCP?